Okay, this month we are looking at Boost.Multiprecision, a library for arbitrary precision arithmetic that can use a variety of backends. So you may be familiar with GMP, the GNU Multi-Precision Library, which is a high-performance library, but it does have the problem that it is a GPL license, and so if you would be using that library, you'd be linking directly against that code, and that would require that your code also be GPL licensed. So there are also other multi-precision libraries out there that you can use, and Boost Multi-Precision gives you a single consistent API to access different libraries, including your own, if you want to plug in your own library. So let's go look at the documentation. It is out on the Boost website. This is the documentation for Boost version 1.88, which is the current version. There are some improvements to Boost Multi-Precision that are coming in 1.89. We'll mention them later. But basically, there's a very good tutorial section here covering multi-precision integer types, floating point types, interval number types, complex number types, rational number types. And I recommend this documentation, their tutorial section. It's not complicated and it's not difficult. It's very well written. It's easy to understand. So I would recommend, skimming through, if you're not going to use rational numbers, you obviously don't need to worry about the rational number types. And then down here in their reference, this is generally the verbose details of methods, types, etc. that are available through the library, through the included headers. Boost Multi-Precision is a header-only library, and as a header-only library, it does impose compile time costs. We will be talking about some of that as well. Now, for my use case, I'm interested in the complex number type. But first, let's talk a little bit just about how this library is structured. So there is a template class called number, and number is your front end, basically your user interface to these multiple precision types. And number is supplied with what's called a backend type to connect the API to an implementation. In Boost Multi-Precision, the implementations are given here as like CPP int, GMP int, Tom int, etc. The ones that begin with CPP, these are header-only implementations provided by Boost Multi-Precision that are licensed under the Boost license. So if you have a commercial piece of software that can't be open sourced, then you can use the CPP types directly from Boost Multi-Precision to get a multiple precision implementation that isn't connected to the licensing terms of GMP. But if your application is open source and you do want to use GMP, then you can plug in GMP as a backend. There's also this Tom math library. They have a backend for the integer types that uses the Tom math library. And it's also possible for you to plug in your own backend by implementing a class that it's not done through virtual polymorphism. It's done through static polymorphism by means of supplying the backend implementation as a template argument. That doesn't mean that you can't call virtual functions. It just means that the way that this Boost Multi-Precision library works is it works through static polymorphism using a backend that implements a concept. It's not a C++20 concept. It's a, it implements the calling interface and semantics described for a backend. So we'll just skim through the documentation here. So this introduction section describes what I was saying. about how there's different backends, and really all you need to do, you typically don't need to concern yourself with the specific backend in terms of like the API of what a backend is. You just include the appropriate header for the backend that you want to use, and then that will supply a type def that you can use. It's either a class definition or it's a type def. It will supply a type that you can use to instantiate variables and invoke math operations using the normal operators, normal C++ operators. Now, as I said, this is a template library, so there is some overhead to the compile time for using this template mechanism, right, to obtain all the operators and all that stuff. It means that all that stuff is going to be expanded out at compile time. Now, there are two ways that you can use the API as a user. You can use what's called expression templates, which is a mechanism whereby when you write, for instance, A times B plus C, and A, B, and C are all multiple precision types, the naive way of implementing that would be to introduce a temporary for A times B, and then add C to it, and then that may in turn create another temporary, a second temporary, and then copy the result of the addition into the resulting variable. Now, because multi-precision types have a data payload that's bigger than the built-in types in C++, like float, int, etc., that may imply heap allocations and reallocations and copying memory from source to destination and so on, and copying of these temporaries. So the expression template support, what it does is take your expression A times B plus C, and at compile time, it turns that expression into basically a little parse tree that is constructed at compile time by constructing instances of template classes that reference the arguments but don't do the computation until the whole thing is evaluated. And since the evaluation happens on the entire expression, A times B plus C, the expression template mechanism can recognize that and possibly eliminate temporaries along the way. And this will return, in turn, because you're using fewer temporaries, it will result in less memory allocations, less reallocations, less copying of memory, and so on. But it does have a cost, and that cost comes at compile time. So Boost.Multiprecision gives you the option of enabling the expression template mechanism or not. And we can see down here, here's a second example. They have this example here. And the second example uses the template argument to supply the template. It instantiates number directly. Instantiation might not be the right word, but it's using the template type number directly, supplying the backend argument, and then it's supplying this ET_OFF argument as the second argument. So that's turning expression template mechanism off. So it saves at compile time, but it might cost you a little bit more runtime, or might cost you a little bit more memory allocation, and so on. They mention in the documentation that as your arbitrary precision number gets larger and larger and larger, it's the cost of the computation that starts to dominate, and not the cost of copying in and out of temporaries. But your mileage may vary with performance requirements. It's always best to measure rather than guess. And if you find that your compile times are unbearable, and the cost of the additional temporaries through profiling and performance measurement is not burdensome, then you can use the front-end API, this number class, with the expression template mechanism turned off. So you have that option. If you don't want to pay for the expression template mechanism at compile time, and the cost of the additional temporaries is not a problem for your performance requirements, you have that option. And this number class is really your user interface to access all of the functionality, regardless of whether we're talking about an integer multi-precision type or a floating point type or a complex number type, they all are exposed through numbers. So that is always an option if you want to turn off the expression template mechanism. You notice here that they are using the MPFR float backend. MPFR is a floating point big num library based on GMP. And the template argument there, 300, that is the specifying the precision of the values that will be used with the MPFR backend. Now, you might be thinking, but wait a minute, my application requires dynamic precision, not a single fixed precision. It's oftentimes that a single fixed precision is what you need, in which case you can specify that explicitly. Like, for instance, you might need to be computing, 1K bit integers. So you can specify exactly that you want 1K bits. The precision as supplied to the backends may be specified as decimals, the number of decimal digits or the number of binary digits. The details of the backend will have that information for you. But if you didn't want a specific precision, you wanted to have an adaptive precision. Instead of specifying a specific number here, you would specify 0. And as we look at the documentation for the various backends, we'll see that they generally supply a couple of convenience types that represent either 50 decimals or 100 decimals of precision. And then they will have another convenience type that represents arbitrary precision, where the precision is specified dynamically. When the precision is specified statically, there is no data used from the heap for the underlying data used to store the arbitrary precision representation. It's stored basically as an array inside the number class. And so you may need to be aware that if you are using a fixed precision backend, that this may have implications for the size of stack that you're using, because variables allocated on the stack allocate stack space. So if you have these large fixed precision values, they're allocated on the stack. There is a way to force them to be allocated off the heap if you want to do that. Basically, you supply an allocator to the back end, and so it will then always dynamically allocate instead of allocating on the stack. But just something to be aware of. Different compilers have different assumptions about the default stack size. If you want to use the stack with large arbitrary precision values, and remember, you're going to need stack space for every temporary and every value that you're using, every variable and so on. So you may need to use a compiler flag to set up the stack size appropriately. So if you want a fixed precision, you just specify that. Like I said, there's a built-in type alias for 50 decimals of precision, 100 decimals of precision, depending on the backend that you're using. And I would suggest, if you want to see through the nitty-gritty of this, their introduction is very good. So let's just take a look. We're going to bounce over to some code here before we just stay in documentation. Let's go over here. And let me bring this window over so you can see this. In my little example repo, I just pulled in their basic example for integer, float, and complex types. If we just look at we'll just take a look really quick just so we can see what this looks like as a user. So they're including the header that provides the types and the backend for their Boost licensed backend for integers. And just a little bit of audio chat there. Okay, so if we just take a look at this, their CPP int header is going to include all kinds of other stuff. The important part important part is if we CPP int, where do they have it inside here? Default ops. Somewhere in this big mess of headers is going to be, looks like that is the implementation. I thought they were going to have their type directly in here. Backends, detail. Well, okay, let's not get lost here, but they provide this type, int 128 underscore t. If we drill into that, we see here we are. Okay, so int 128 is a type def for the number template class instantiated with the CPP int backend, and these numbers here are representing whether it's a signed integer, an unsigned integer, and how many bits are used for the mantissa, how many bits are used, if it's a floating point type, how many bits are used for the exponent. For an integer type, there's no exponent given. It's just the number of bits for the mantissa. Whether the type is checked or not, and what the difference between a checked and an unchecked type is that a checked type throws exceptions if it overflows or underflows and things like that. Otherwise, the unchecked type, the semantics are different for the different kinds of arbitrary precision types. For integer types, it typically means that if you overflow, for instance, it goes from the, and it's say it's an unsigned integer type and it overflows, it goes from the maximum unsigned value and rolls around to 0 and then continues on from there. So I would say probably want to use the checked types in a debug build or while you're developing. And then if you, like your runtime requirements are such that you can't use exceptions or anything like that, and you're confident that your computation is not exceeding any of the bounds or requirements of the types, then you can go with the unchecked type and avoid possibly throwing exceptions and having to worry about that. But basically, you use these types, and just like any other type that you would use to declare variables, they have constructors and assignment operators that allow conversions that are preserving, so they don't lose precision. They have conversions from the built-in types. So for instance here, they could take this 128 int, 128-bit int, and just assign 1 to it directly. They didn't have to worry about explicitly converting that constant 1 to 128 int 128 underscore t. They could just do that directly. And the same goes for, they can just multiply that in onto the value, and there are stream insertion and extraction operators provided for all these types. And here they're using the arbitrary precision. So this int 128t, that was defined as an integer with 128 bits, and here they are using the arbitrary precision int. If we drill into that type, we see that it is a number instantiated with the CPP int backend, and the precision argument is just empty. Some of the backends require you to supply 0. Some of them you can use empty, or maybe they all accept empty. I didn't test that. But same thing. It's arbitrary precision. Here, they were doing basically 20 factorial, and that was the biggest one that would fit into 128 bits. Here they do 100 factorial, and because it's arbitrary precision, it grows to whatever size is necessary to hold all the digits. And again, you can just insert those into a stream or extract them from a stream. Now, it's very similar for, if we look at the floating point example, it's very similar. Here they're using, as I mentioned, they have predefined types for 50 decimals and 100 decimals. So here's their binary float, our big num type, And again, this is using the one with the Boost license. So that's already included inside Boost Multi-Precision. I don't have to get another library. It's built in. If you want to use the other backends like the GMP backend, then it's up to you to go and get GMP and make sure that it's available to Boost Multi-Precision when you um, include the header for the GMP backend or whatever other backend that you're going to use. But these CPP backends, they're all included with Boost Multi-Precision, so you don't have to get another library to get those backends. They're included and provided under the Boost license. So this CPP bin float 100 is a type alias for number instantiated on the CPP bin float backend with 100 decimals. Uh, it might be 100 bits. I think it's 100 decimals. Sorry. And similarly, here's like the 51, the 50 decimal one. So as I was mentioning, this sorry, not the number class, but the backend class, it has a template argument that says what the base is of this digit's value. I believe it defaults to 10. You can specify, if you want to specify the size of the value in bits and not decimal digits, you can supply an additional template argument to specify that your precision is specified in bits and not digits. Let's go back here to the example. And again, very similar, kind of work. We're, creating a variable, doing some IOStream operations, and printing it out, calling a function. Now, what is interesting is that they provide implementations of all the standard math functions, and they also have Boost math support. Now, I am picking up Boost Multi-Precision through VC Package, and any of Boost Multi-Precision's dependencies are brought along by VC Package. So Boost Math is brought along, which is why this call here is syntactically valid and compiles just fine. And that's nice because Boost Math implements more functions that are not necessarily in your standard library. They've added more of these functions to the standard library over time. But the wrinkle with these math functions is that math functions in the standard namespace, you cannot extend the standard namespace by adding overloads into the standard namespace. You have to add overloads into some other namespace. So what they do is they have added overloads for the multiple precision types of the math functions into the Boost Multi-Precision namespace. So this call to log here, this is actually calling Boost Multi-Precision log. They've implemented in this default ops.hpp, which is in a detailed subnamespace of Boost Multi-Precision. Now, if you're writing your own code and you've decided to take the type of the arguments, let me state this another way. Suppose you wrote your own template function that you want to call log, but sometimes you want to have it call standard log because the template argument is double. And other times you want to have it call Boost Multi-Precision log because the template argument is a Boost Multi-Precision type for floating point, for a multi-precision floating point type. How do you do that? We'll see how you do that when we look at my example where I've got some code templated for computing Mandelbrot set. I'm using either std complex of double or I'm using std complex of well, I'm using the complex type provided by Boost.Multiprecision. But basically, it amounts to you do a using statement, and then the function call is not qualified by namespace, and then the using statement brings the appropriate namespace into visibility for that function, and then it selects it through overload resolution and picks the right one. It's a small trick. We'll see what that looks like when we look at the example code here. But the main point is all the math functions have implementations provided, and the Boost math support gives you access to additional functions beyond those in the standard library. If we look at their complex example, this one we'll see the using trick. This one prints quite a bit of output. Does a bunch of different things with complex numbers. Here you see they do that using trick where they say using stood abs for absolute value, and then when they invoke the function, they don't qualify the function name by its namespace. So this using statement brings the abs function from the standard namespace into visibility inside this function. So when we call abs here, it will pick the right one based on the type of the argument. The type of the argument is passed as a template argument to this template function, so that down here inside main, it invokes that function once for stood complex of double, and then it invokes it again with a complex type from Boost.Multiprecision. So that's why up here, all the function calls are not made with respect to a namespace, and a using statement to bring the overload from the standard namespace. That's the overload that gets used for stood complex of double. This brings that overload into the set of functions that will be considered for operator overloading or function overloading by the compiler. And so if Z1 here is a stood complex of double, then we end up calling stood exp. But if it's a CPP complex quad from Boost.Multiprecision, then we will call Boost.Multiprecision exp. So just a little something to be aware of when you write your own code, if your own code is templated on the data type. Okay, so if we take a look at the specifics of these backends, there's a bunch of stuff describing the template arguments that this backend accepts. So in the case of an integer, this CPP int backend, it has a minimum number of bits, maximum number of bits, whether the type of the sign, since this is a signed integer, whether it is, because this backend can support signed and unsigned integer types, this template argument, the signed type, says, is it signed magnitude representation or is it unsigned magnitude representation? This checked argument, as I was mentioning before, that determines whether or not operations that exceed the limits of this type result in exceptions being thrown, or whether they just result in some other behavior that is documented for the back end. And again, the allocator is when the either because you've got a fixed precision type and you want to use memory from the heap for the data associated with the value, or whether you've got a dynamic type, in which case the allocator is used to always allocate the data off of the heap. And then you can see here that there's a bunch of type defs for the different types that are supplied by this backend. Fixed precision unsigned types, fixed precision signed types with checking. So these checked CPP ints are with checking enabled. So again, all those types are repeated with checking enabled. and then just the CPP int with no other decoration. That is the arbitrary precision integer type. And all those template arguments are explained in the back end. And here's what's happened here's the behavior of what happens when it's a checked integer type versus an unchecked integer type. And then there's some details of things that you should know about, how this type behaves. And then here's that example that I've copied into my little example repository. So really straightforward to use this library. You just want to read through for whatever type you're interested in. You want to read through the different backends that are available to you. Obviously, like a GMP backend or an MPFR backend require the GMP or MPFR libraries to be available. Boost.Multiprecision doesn't handle obtaining those libraries. That is up to you. This Tom int backend is for this Tom math library, which is another multiple precision integer library that's been around for a while. Now, I mentioned that there were some changes coming in Boost 189, which is on its way to being released right now. The current release of Boost is 1.88. And what's interesting there is they're going to be providing a so-called double-double implementation for floating point types. Now, what's a double-double? Well, it turns out that you can extend the precision and range of hardware-supported double by combining two doubles together. And the algorithms are well-defined. It's not quite as much precision as a 128-bit IEEE floating point value. Doubles in most compilers by default make a double a 64-bit value. If you're compiling for 64-bit code, I think even in 32-bit code, a double was typically 64 bits. But the x86 CPU does not directly support hardware math on 128-bit floating point values from the IEEE standard. Other CPUs may provide that, but the x86 and x64 instruction set does not. So you can get more precision and range than a double by combining two doubles together. And they have merged into their develop branch to be released in 1.89 basically a CPP double-double type for floating point values. And you get much better performance with double-double than you would get with these arbitrary precision float types. So just something to be aware of if you're... Oops. I am always doing that. I meant to do Alt left arrow. So that is something to be aware of if you're interested in double-double support as a backend for floating point types. Now, the floating point types that are provided, the floating point backends, they basically become the underlying representation for a complex number. So if we look at CPP complex, basically they're the type that they use for the two floating point values to represent a complex number is basically coming from the float backend. In this case, the CPP complex number type uses the CPP bin float backend to represent the two values making up a complex number. Now, there is also a library called MPC. MPC is a complex, arbitrary precision complex number library that is built on top of GMP or MPFR. I think it's built on MPFR, and MPFR in turn is built on GMP. So if you want to use complex numbers with the GNU multi-precision libraries as the backend, that is certainly doable. In our example that we'll be looking at, I'm using the CPP complex backend. And again, this example I've copied into my repository, but I've also got my own code that we'll be taking a look at. Um, there's also an interval number type, and if you're not familiar with interval arithmetic, the idea is that instead of just representing a single floating point value, there's a floating point value with and basically an error interval that brackets that value that indicates, it's if you've ever done like, computations in quantitative chemistry, they often have you do things like you write down the value that you measured, but you also record the error of the measurement. So it's, 15 grams plus or minus zero point 0.1 grams, when you measure the mass of something. You measured it at 15 grams, but your scale was only precise to plus or minus zero point 0.1 grams. So you're recording a measurement, 15 grams, and you're recording the error bars, plus or minus zero point 0.1 grams. So an interval type encapsulates that directly, and interval arithmetic does the proper computation to propagate the error value along. So when you do some kind of combined calculation, you know what the error is in the result, and based on the error in the inputs to the computation. So interval number types can be useful in that kind of work. Again, we mentioned the complex number types, rational number types. This represents the ratio of two integers as opposed to a floating point value. And we see that the TomMath library also provides a rational type that can be used as a backend. This rational adapter lets you take any other integer backend and use it to create a rational number type. This description here about constructing and converting between number types. If for whatever reason you need to do a lossy conversion, you will not be able to do that directly. You will have to express that explicitly so that the library prevents you from accidentally losing precision. So you either have to do a static cast from the higher precision value to the lower precision type in order for the assignment to be acceptable, or you do there's an assign function that you can use as well. There's also ways that you can do an explicit conversion from a multi-precision type to another type specifically if it can't be deduced from context. Like if you need to explicitly convert a high precision, you have a high precision integer, but you know that it's going to fit into an int, so you can explicitly convert that into an int, even though technically that's a lossy conversion. There's support for Boost serialization. The really good element, and we'll see this when we get to my little example here, is that numeric limits has been specialized for these types. So that is a specialization of a template type that's allowed by the standard library. You're allowed to specialize standard numeric limits for your types, and that lets you get at things like, what are the number of digits representable by that type? What are which, if you're using a fixed precision type that was like only available through the template argument, there might be an accessor on number that lets you get at that. But basically, with numeric limits, it gives you a way to glue into existing algorithms that are maybe template algorithms, but they have to know certain properties of the values that they're manipulating, so they get those properties through standard numeric limits instead of making an assumption, or instead of using the old, L double min or something like that macro from C style code. There is also hash function support. And basically what that means is you can use map or other unordered containers to hold arbitrary precision values as keys. So those containers hash the key, and it's the hash that they keep around in the data structure. So the hash function support allows you to use these multiple precision types as keys into these hashed containers. There's also Eigen is a popular library for matrix manipulation. So if you want to do matrices of arbitrary precision types, there is Eigen interoperability for doing that. There's some discussion here of how to write a new backend, which we're not going to go into because that's low level details that we don't. The number of times you need to write a new backend is probably one time in 10,000 that you're going to use this library. But the information's there. They have basically a skeleton that provides you with everything that you need to get going on, and you can fill in the skeleton. This reference section here is where we start drilling down into all the nitty-gritty of these headers. So here's all the members of the number template class. The number template class takes a bunch of template arguments, and you notice these things like unmentionable expression template type, and that's basically saying there is a global operator plus, and it returns some type that's an implementation detail, and the type of the argument that it accepts is also generalized into it's not so much an implementation detail such that it is generalized in such a way that it does all the things that you would expect, all the normal things. And then there's this list of all the functions that they support. Most of these are in the standard library as well. For some I didn't realize were in the standard library, like cubed root. I didn't realize. I knew square root was in the standard library. I didn't realize cubed root was in the standard library. Erf is the error function. There's a bunch of other functions provided, so not every function they have listed here is necessarily in the standard library, but a bunch of them you will recognize as coming from the standard library. And then there are also some functions you may recognize from std complex in the standard library that are, for instance, the real function takes a complex type and returns the real component of the complex value. There's some more down here, greatest common denominator, and so on. So to see if you are using specific math functions and you need to know if they are supported, consulting the reference for number would be the first place to look. But because there's also Boost Math support, I thought they called that out in a separate page, but because Boost Math is also supported, you may want to consult the documentation for Boost Math. Okay, so I'm not going to go over every little bit of the documentation. It's very good. It's complete. I didn't find anything missing. I found a few little minor typos and a few. This library's been around for a while. It was first introduced in Boost 1.35 or something. It originated in 2002, so this code's almost 25 years old. So it's been around for quite some time. But overall, the documentation's very good. I did find a few little typos and some old stale links and stuff. I filed bugs on that. They're going to try and get those fixed for 1.89, which I said is in preparation now. Okay, so let's take a look at my example. My example is I've just got a little console program that's going to do a bunch of zooms into the Mandelbrot set, and we're going to see how you write a template function that works either with std complex of double or std complex of my little type alias CPP complex here is the 50-digit precision CPP complex. So let's take a look here at, oops, Wrong keystroke. Let's take a look at my header file. So here is my Mandelbrot loop, and I've written it as a template function where the first argument is the type of the complex value. And sometimes I need to hold a complex, and sometimes I need to hold one of the components of the complex. So I am doing a little trick where I'm saying the second template argument to this function is the type of the value that represents one of the components in the complex number. And I am defaulting that to the nested value type alias inside whatever that first argument is. And I have to use the type name keyword here. I mean, here I could have written class instead of, let's just make sure so this doesn't get in the way. Let's just make sure Copilot chat suggestions are off. Okay. I could have written class here, but here this has to be type name. So it's kind of a little bit confusing maybe if you haven't done this before, but I'm using type name in two different contexts here. When you're describing a class argument, a type argument to a template function or template class, you can write either class struct or type name. I tend to write type name. That's my habit. It's here the type name, the use of type name is not required. I could have written class or struct or type name. All three are acceptable. Over here, this is the other use of type name. And here, the keyword type name is required. And what I'm saying is that this identifier, this value type identifier that's nested inside this other thing called complex, that names a type. It's not a function, it's not a value, it's not the name of a field, it is the name of a type. So in order to disambiguate this nested name, because at the point where this template function is parsed, we don't know what the first template argument is going to be. We don't, if it's int, then int double colon value underscore type is ill-formed, right? So that's bad. We don't know what this is yet. And so this is just the other use of type name to specify that this identifier that is related to another template argument is indeed the name of a type. And the reason that I do that is so that I can say my first argument to this function is a complex number, whatever representation. And the second argument is compatible with the value of one of the elements of the complex number. So it's compatible with the real or imaginary values that are in the complex number. And that's because I'm going to do some math. And I was a little surprised here that I had to qualify this constant as I had to cast it to type value. I was getting an error about operator divide. So it worked fine when this complex here was a stood complex of double. Worked fine. But as soon as I supplied the Boost.Multiprecision complex, then I had to qualify this constant over here as cast to the type of the two values inside the complex number. I'm not, honestly, I thought that was just going to work, but it's a problem that's easily solved. Down here, I'm doing something similar. This is all scalar math, right? I'm not doing complex math yet, but here I'm taking my integer argument and I'm casting it to a value so that I can do floating point divide. I want floating point divide. This value here is a floating point value. So just casting that, static casting that. I mean, here I did static cast and here I did kind of function cast. So, pick your poison, which one you want to do. But I had to explicitly convert them to a value in order for that expression to work, which was a little surprising, but not a big deal. And then I am basically walking over a grid of samples. I'm going to, the Mandelbrot set is take a complex number, you square it, add it to, and add a constant to the number that you squared. And then you compare the magnitude of that to the value 4 to determine if it's going to basically iterate, escape. It's what they call it, is escaping to infinity. So it's a sequence of numbers that you compute. If the number, the magnitude of the number exceeds a certain value, then it's considered to escape to infinity. Otherwise, we have to keep iterating to find out, and we may reach a maximum iteration count before we've determined if this sequence escapes to infinity or if it does something else, like maybe gets stuck in a loop and just repeats the loop over and over and over. I'm not doing any loop detection here. But if it did get stuck in a loop, I don't want to keep computing. It'd be infinite computation, so it would never escape. And that's, I just extracted this into a little bailout formula. So here's the thing saying if the norm of this function, of this value z, so the norm of a complex function, sorry, the norm of a complex number is the square of its magnitude. So the reason we're using norm instead of its the magnitude, because magnitude involves computing a square root. So if we can compute the norm, which is just the real component squared plus the imaginary component squared, we compare that to our escape criteria, which is 4. That avoids the square root, and so we can get a little bit faster. And so here's the formula. Like I said, you take the z value, the complex value in the sequence, multiply it by itself, add the constant, and the result is the next iteration. So for every iteration, I'm checking to see if we've bailed out, if it's escaped to infinity. If it did, we're going to break out of the loop. Otherwise, I'm going to iterate one more time. Once we get out of the loop, I'm just going to record the number of iterations at that point. I'm going to advance as I go across the scan line. I'm advancing across the real axis as I go up the y-axis. I'm increasing in the imaginary axis. So as my y loop increases, I'm going up by some value di. Now, this real number here and this imaginary number here and these little di and dr values, they all have to be arbitrary precision, because as I zoom into the complex plane, I'm eventually going to run out of precision in a double, and I'm going to switch over to the 50 decimal CPP complex type. And that's why this value has to be used instead of double, because I have to do these, I have to keep these numbers in arbitrary precision. So we saw down here in my little bailout function, I had to do that using trick to get the norm function brought in, so that if I was calling it on stood complex of double, which I made a little typed f up here called d complex. If I was invoking it on d complex, I need to make sure I get stood norm. And if I'm invoking it on a CPP complex, I need to make sure that I get the one from Boost.Multiprecision. So my little program, my main function, my main function, we're going to start out with doubles. And our center point is going to start out as a complex double. And I'm going to run this code where the complex type is stood complex of double, and then my value type will be double. I'm going to construct a little result image by calling that plot function, which is the function we just looked at. And then I'm gonna write it out to the console. This little report function, it returns true if basically the image didn't have enough different iteration counts in it, which implies we're hitting our iteration limit very frequently. So when that happens, I'm just going to increase my maximum iteration count by doubling it. I'm going to, the way this little zoom function is working is we're going to render an image and then we're going to magnify by 2. This magnification factor actually represents the size of the region of the complex plane that I am sampling. So I'm taking the magnification and dividing it by 2. Maybe magnification has got the backward sense of the semantics here, but that's how it's working in this code. And I just got a little pause option in here so I can, when I was debugging it, I could see the result of the images as they were getting computed. So in a release build, what this looks like, let's take this breakpoint out. If we run this, it's going to do some building because I was typing in the files. So if we just pause this, we see here's 256 iteration count. This is my magnification factor, and here's my little ASCII images being printed out. And it got slower. Maybe you didn't notice because I had it paused. Let's run it. It'll be more obvious when we run it in debug. Let's run it in debug. Okay, so here's an obvious transition from when we switched to complex of double to complex of the multiple precision type. And I'm not printing out the full, digits of precision here because I didn't call set precision when I output this magnification factor. It runs out of steam with the double type at about 10 to the minus 18. And then there you just notice that here everything was just basically one iteration. So we increased the number of maximum iterations from 256 to 512, and then the next image became much more detailed again. It's not necessarily the best adaptation of these parameters as I'm chunking through this, but it's better than having these images all just be like a single character after a certain point. I didn't want to, again, because I'm not doing periodicity checking, I'm not doing loop checking for cycles. I didn't want to do like 1024 iterations on every single sample because I'd just do a whole lot more math when you get stuck in a cycle. You're just going to do 124 iterations every single sample that is in a cycle. So this is going to stop in a little bit. I think 10 to the minus 38. Let's Control C the debug one and run it again in release. Now that you saw the obvious transition, the slowdown as we switched from stood complex of double, which can be completely evaluated in the hardware of the CPU, over to the multi-precision type, which has to go through a software algorithm. Whoops, we didn't want to do that. Let's get the main back over here. We wanted to do Control F5, not Control F4. So we're in the multi-precision range now, but this is a release build, so it's not taking ridiculously long. It is still longer than, obviously, than the stood complex double. And I believe this is going to bail out soon. Yes, so it ended up increasing its iteration count, maximum iteration count to 1K. And you can see here, it's still, we went from this image, which has a lot of detail in it, to this image, which looks really like I need to increase the maximum iteration count again. Or it's just because we've reached the limit of the precision of the 50 decimal floating point type. Now, you might say, like, how did I know to do that switch And the answer is here. I'm checking my loop here. I'm going to keep zooming as long as the difference between my current magnification factor and my last magnification factor is greater than 10 times the smallest representable difference in the type. So if you're not familiar with this numeric limit stuff, epsilon, let's go over here and go to CPP reference and go to epsilon. Standard numeric limits. Epsilon returns the machine. Let's make this a little bigger. Returns the machine epsilon. That is the difference between 1 and the next value representable by the floating point type t. So here, epsilon represents basically the smallest value that's different from 1 in this floating point type. And I'm saying if my magnification factor is, or the difference between two magnification factors is smaller than epsilon times 10, then it's time to switch representations and go to a higher representation. So this zoom loop, I first did it with stood complex of double, and my magnification factor represented as a double. I did that. I ran that loop until it ran out, and then it told me what the maximum iteration count it got at the end, because it was taking these. If we go to this zoom function, the max iter and the magnification are accepted by reference, so it's modifying them and communicating that back out to the caller. And then I just pulled it into a different little helper function here, where I have the lower precision value of the current center point, the lower precision value of the current magnification factor. I construct higher precision values for the center and magnification factor, and then I invoke the zoom loop again, passing along the pause and the max iter that was passed into me. So this is basically, I kept zooming in until double ran out of steam, and then I zoomed in again until this 50 decimal complex float type provided by Boost.Multiprecision until it ran out of steam. Now, these fractal algorithms that I've been using here, they're extremely stupid and naive, and they don't check for cycles. There are other significant speed ups that you can get to this computation from the fractal computation side. There's an algorithm called perturbation, and there's other simple things you can do to improve the performance of this algorithm. So all I've done is just written the naive implementation that ran the complex of double until it ran out of steam, and then I switched over to multi-precision and continued on. And by writing the algorithm as a template function, I didn't have to have code duplication for the version that ran on doubles and the version that ran on the multi-precision type. So that is my little example, and if you clone this repo from GitHub, you'll get the little examples that come from the Boost Multi-Precision documentation. Obviously, you can clone the Boost Multi-Precision repository yourself. It is on GitHub. All the libraries for Boost are now on GitHub under the Boost.org umbrella, and then the individual libraries. I think most of them, if not all of them, are now homed under Boost.org here. So if you want, latest and greatest stuff from GitHub, Bleeding Edge, you can get that. I'm just using VC package to obtain things. So I just said I need Boost Multi-Precision, and then that brought in whatever other Boost libraries were required by multi-precision. I didn't worry about managing all those dependencies myself. Makes it very easy to consume this. Again, and it's a header-only library, so you don't need to worry about compiling it. In my code, to get access to this, I just do find package boost underscore multi-precision required config, and that got me this imported CMake target that I could link against, so my include directories were all set up correctly. Another way to do it is to do find package boost config and specify components multi-precision. That also gets you the imported target for the multi-precision library. And the way this works with VC package is because I installed the dependency with VC package, everything was available in terms of all of the dependencies of Boost Multi-Precision. So that is this library in a nutshell. If you, let's go back here to the documentation. If you want to use the GMP backend or the MPFR backend, it's really not any different than what I've shown here using the built-in CPP backends that are Boost licensed. The only difference is, of course, you have to compile GMP or MPFR or whatever dependency you're going to use. And if you were to do that with VC package, it would be easy. But I will warn you that it takes a significant amount of time to compile all the stuff in GMP or in MPFR or in MPC. At least VC package will orchestrate all that for you, but you will have to wait for all that stuff to be downloaded and built. Obviously, with template functions and template algorithms, it can cause compile times to keep leaking through into any translation unit that needs to include that header. So if you find yourself using template algorithms, my advice would be to build a compiler firewall by creating a non-template API to access those algorithms at a high level so that you can isolate the header inclusion and compile overhead of Boost Multi-Precision and your templated algorithms that are layered on top of that. Isolate that and get it focused into one place so that the compile times for every single translation unit in your whole project don't balloon out of control. But that's just standard template library, management. Nothing new there. Nothing specific to Boost Multi-Precision. So that's the library. The authors are responsive to issues that you file, so that's always good to know. That means the library is currently being maintained and worked on. There's good discussions that can be had if you have a problem, and that's always a good sign for a library. It means that even though this library has been around for almost 25 years, people are still working on it and participating and contributing to it. And that's all we have for this week, or this month.